Okay, in today's lecture, I'm going to show you a very clever trick for proving statements like, for instance, this example. 1 plus 2 plus 3 plus so on up to n equals n times n plus 1 over 2 for any integer n equal to or greater than 1. That's a handy formula. For instance, if you wanted to add up all of the numbers from 1 to 100, I'll tell you right now that's 5,050, because I just have to do 100 times 101 over 2, which is 50 times 101, which is 5,050. This is a very neat formula. Okay, I'm going to show you how to prove things like that. So let's start off with this idea. There is something called the principle of mathematical induction. Okay, here's what it says. Let P of n be a property that claims to be true. Well, let's say it like this. Be a property about some integers. Okay. Now, suppose number 1. Suppose P of A is true for some integer A. And number 2, if K is equal to or greater than A, and P of K implies P of K plus 1, okay, then I see I should not have put the word if here, because I have the word suppose here. That's my if. So let me erase that. I will actually choose to reword this slightly. Let me take this pk implies pk plus 1. Let me shift that over and then say for some integer k equal to or greater than a. And you might prefer the word any instead of some. That's fine. So suppose those two things. Suppose P of A is true, and when P of K is true, we automatically get P of K plus 1 being true. Okay, then in that case, P of n is true for all integers starting with A. That's the principle of mathematical induction. Okay? So when we try to prove this in a few minutes, what is it that we will need to do? So in this case, our A is 1. And this is our P of n, is that formula right there. And what we will need to do is show that that formula is true for the number 1. In other words, 1 equals 1 times 2 over 2. And we will show that if that formula is true for some random integer, which we'll call k, then it also has to be true for the next integer, k plus 1. So we will show that it's true for 1, and that if it is true for one integer, then it's also true for the next integer. And those two things together means it'll be true for every integer starting at 1. Okay? That's called proof by mathematical induction. Okay, let's write that down as a separate thing. Proof by induction. Okay, so in order to prove that some statement P of n is true for all integers equal to or greater than a, comma, we can do this. Step 1. Show that P of A is true. Step 2. Show that P of K implies P of K plus 1. How do you do that? You suppose P of K is true for some integer K equal to or greater than A, and then you show P of K plus 1 must also be true. And then you're done. Okay? I'll finish off here by saying, then P of n is true for all integers n equal to or greater than a by y? By the principle of mathematical induction. We'll just write by PMI. Okay, that's proof by induction. Very helpful tool when you're trying to prove something is true for all integers starting at some point. A little bit of vocabulary for you. This part, step 1, is usually called the base case. And the first part of step 2 is called the inductive hypothesis. Okay. The base case is usually very easy to prove. It doesn't have to be. There's no rule about that, but it almost always is very easy. The inductive hypothesis, there is no work whatsoever. It says, suppose. You're not actually proving anything. You're just assuming something. So there's no work whatsoever to do other than to just write the sentence down. All of the work happens here. Okay, so let's just do some practice on this. So let's prove the statement that I wrote at the beginning. Okay. Prove that the sum of the integers from 1 to n equals n times n plus 1 over 2. And we're going to prove that that is true for all integers starting with the number 1. Okay. So, the first part we're going to do is, I'll write in gray some notes just to help us. First thing we're going to do is, well, let's call this P of n. And the first thing we're going to do is show that P of 1 is true. And that's something you have to actually do. That's some work you have to produce, but it's usually really easy. Okay? 1 equals, and then I just have to fill in some steps there to show that it equals 1 times 1 plus 1 over 2. Okay? And you can see how easy it is to get there. Because 1 equals two over 2, right? Which equals 1 times 2 over 2, which equals 1 times 1 plus 1 over 2. Now, why did I write it this way? Why didn't I just write it this way or something like that? Because I'm looking at my statement, and my statement is on the left-hand side, it's got the sum of the integers from 1 to n. So when n equals 1, that's the sum of the integers from 1 to 1, which means that's just 1. That's the left-hand side. Okay? The right-hand side is this. N times n plus 1 over 2. And in this case, the base case, it's the first step. N is 1. And this says n times n plus 1 over 2. So I need this to say 1 times 1 plus 1 over 2. It should match. The format of the left side should match. The format of the right side should match. And then you just fill in whatever you need to in the center to get from here to here. Okay? Very little work to do at all, but you do need to make sure that it's written the way it's supposed to be written to match what is written up above. Okay? All right, so that's step 1. Step 2 is to show that P of k implies P of k plus 1. So what do I write? You don't have to write what I'm putting in gray. Those are just some notes to help us. Only what I'm writing in black is what's mandatory. Okay, so what should I write? I say suppose P of K. What would P of K be? P of K would be this. Okay. For some integer K equal to or greater than, what is our beginning value in this problem? It was 1. So I put for some K equal to or greater than 1. Okay? Now again, there's no work to do there. It's just a matter of writing that sentence down. So don't get lazy and try to cut corners. Write down that whole sentence. Okay? That's all you're being asked to do is write it down. Okay, then, and now I need to show that pk plus 1 would have to be true. In other words, I need to show that 1 plus, well, the sum of all of the integers up to k plus 1. I need to show that that's going to equal k plus 1 times k plus 1 over 2. I need to show that, though. It's not obvious. That's going to take some work. So what I have to do is fill in all the math in between. Okay? And it's probably going to take several steps. So to be honest with you, it will probably end up looking more like this. It'll probably end up looking more like this. But definitely, it's got to start that way. It's got to end this way. You have to show how to link those two together. And I'll point this out as well. You have this to help you, and that's usually where the trick lies. So let me show you how I would bridge the gap in this problem. So I'm not sure how many steps it will take, but I'll just go ahead and leave those equal signs there. If we need more, we'll add more. If we don't need as many, we'll delete some. The first thing I would do is, and here's a hint for you, you want to use this. So here's what I'm going to do. I'm going to take the sum of the integers from 1 to k plus 1, and I'm going to rewrite that like this. I'm going to go from 1 up to k, and then plus k plus 1, okay? And then this part I can replace with this. So that would equal k times k plus 1 over 2 plus k plus 1. Okay. And now I just want to add those together, and hopefully I will get something like that. Let's just do the addition. Okay, I need a common denominator. So that would be k times k plus 1 over 2 plus 2 k plus 1 over 2. Let's add those together. Let's see, we're going to get k squared plus k over 2. We're going to need some more room here. That's okay. Plus 2k plus 2 over 2, and so we can add those together now. We get k squared plus 3k plus 2 over 2. Let's factor the top. It factors into k plus 1 times k plus 2 over 2. And then I just write that k plus 2 as k plus 1, which I already had written there. Sorry, I didn't mean to erase so much. Okay, and that's the whole proof. That's the end. I'll put a little box there to signal that we're done. Okay, it's not difficult. It's not difficult at all. This part, I'm just repeating myself. This part is usually easy, but this needs to match this, and this needs to match that. Okay, otherwise I won't give you full credit. You gotta put in that amount of effort, okay? And this requires zero work at all. It's just a matter of writing down the proper sentence. So far there's been 2 steps. One is very easy, requires very little work, and the second one requires no work. Okay? And then you do this part, which is where most of your work is. It's usually not difficult though. Once again, this needs to match this, and this needs to match this if you want to get full credit. Okay? Let's practice another one. Okay, look at that statement. If r is not 1, then, do you remember how to read that? That is the sum, that's what capital sigma stands for, of r to the power I, where I starts at 0 and goes to n. So that is r to the 0 plus r to the 1 plus r squared plus r cubed plus so on and so on up to r to the n. That's what that yellow stuff on the left hand side means. Okay, and we want to prove that that equals this for all integers n starting with 0. So let's prove that by induction. Okay, it'll be just like last time. It's not going to be difficult. You just need to follow the format. I'll leave the left side highlighted yellow and the right side highlighted green. Okay, this formula is our statement P of n. Okay, so step 1 of the proof is show that P of, what's our starting point this time? It's 0. Show that P of 0 is true. So what would the left-hand side of P of 0 be? Well, it would be this, stopping at what point? Stopping when the exponent is 0. In other words, it would just be that first thing. Okay? So it would be r of 0. That's the yellow part. I must show that that equals the green part, which would be what? The green part would be r to the 0 plus 1 minus 1 over r to the 1. I mean r minus 1. Okay, that's just a matter of just copying down the yellow part and the green part, inserting the number 0 in place of n, and then I just have to do some math to bridge that gap. Okay, and it's usually very easy math. So what's r to the 0? R to the 0 equals 1, doesn't it? And isn't that equal to r minus 1 over r minus 1? Which is r to the first minus 1 over r minus 1, which equals r to the power 0 plus 1 minus 1 over r minus 1. So I'm done. Okay, see, that requires very little work. Okay, the second phase of the proof is show that p of k implies p of k plus 1, where when k is any integer equal to or greater than 0. So we write the sentence, suppose this yellow stuff when n equals k equals the green stuff when n equals k. For some integer k equal to or greater than 0, because 0 was our starting number. Okay? No work to do there, it's just a matter of writing down the sentence correctly. Okay, then so we need to show that p of k plus 1 will also be true. What would the yellow side look like when n is k plus 1? It'll look like this. And what will the green side look like when n is k plus 1? It'll look like this. So when I give you some homework problems on this or test questions, I'm going to look to see if you have this at the beginning and this at the end. If your yellow and green don't match the yellow and green up here, you're not going to get full credit, okay? I don't expect a lot, but I do expect certain things. Okay. Now, the trick is to fill in the gaps in the middle there. And remember this hint, the key will almost always be to use that. Use that as the key. Okay, so let's figure that out. First thing I'm going to do is let's just take this part here and let's just move it down. It'll probably end up being down here somewhere, and we'll probably have a few steps to fill in to get there. Okay, let's figure out the steps. Okay, well, where do we start? Now, why don't we start with writing down what this looks like? Okay, that's a good place to start. It looks like this. R to the 0 plus, and then r to the first, r to the second, and so on and so on. And we would stop when we get to r to the power k plus 1. Okay, now notice that that would equal this. Correct? I'm just saying that the number that comes right before r to the k plus 1 is r to the k, right? And don't I know what this equals? Whoops, sorry. Don't I know what this equals? Isn't that this? So doesn't it have to equal this? So we have here r to the k plus 1 minus 1 over r minus 1 plus r to the k plus 1. You see how I used this formula right there to replace, here let's use a highlighter, to replace this with this. Okay? Now I would like to do this addition right here. So I need a common denominator. So we'll write r to the k plus 1 minus 1 over r minus 1 plus r to the k plus 1 times r minus 1 over r minus 1. Okay, which would be r to the k plus 1 minus 1 over r minus 1 plus r to the k plus 2 minus r to the k plus 1 over r minus 1. Do you see what I did there? I just distributed here, that's all. Now let's do that addition. Notice that these two things cancel. So we just are left with r to the k plus 2 minus 1 over r minus 1. And now I'm done because that perfectly bridges the gap between here and here. So we're done. Okay, it's a very handy trick. And once you get the hang of it, it's pretty routine. It's not very difficult usually. It's because it's the same pattern all the time. Okay, now we have no lectures next week because it's the whole week is off for Thanksgiving, so this will be the last lecture for about 9 days.